This is a walkthrough of the software I modified for my tracker, which is a PS3 controlled mini Skidi. This is based on the hardware designs and the code released by Professor Boots for the mini Skidi version 2 that you can find in GitHub. The PS3 clone controllers are available at AliExpress. They're pretty cheap. I think I got mine for $8 Canadian. The only problem is you need to make a setting change inside the controllers to work with the ESP32. The ESP32 has a Bluetooth MAC address, and so the controller is going to communicate with the ESP32 using Bluetooth, but it needs to know the MAC address of the Bluetooth transmitter in order to pair with it successfully. To do that, you need to run a Windows 11 tool. So if you're in a Mac OS, you've got to borrow a Windows machine, and you run a little utility called 6-axis pair tool, and you can set the MAC address inside a PS3 controller. You'll then need to change your ESP32 to that same address. What you're really doing is telling the PS3 controller, I want to pair with this MAC address. And I'll give you an example MAC address there that I've used, 1A, 2B, 3C, 01, 01, 01. You can't use just any MAC address. Some MAC addresses are broadcast addresses, and you can't set an ESP32 MAC address to a broadcast address, but the one there works fine, and you can change the 010101 to 02 or 03 or 04 depending on how many controllers that you want to use with various devices. So the feature of the code that I modified is mostly it has a proportional signal to control the drive motors, so I can control the speed moving forward and reverse and also turning. It also allows easier setting of the endpoints for servos. You want to make sure that your servos don't hit a hard stop or trying to get beyond a point that the hardware will let them, or the servo may burn out. It also supports a LED bar on the forward of the cage, or a red flasher on top if you wish to make that. You can also, however, set the throttle to be non-proportional, just the normal full speed ahead or stop. If you don't have a flasher, it's very easy to control all these settings by turning them on and off just with a couple of variables in code. Uses a debug feature to disable serial.print statements for when you don't need them. Once you've got your code all set and you're running your Skidi from batteries, you don't need to use the serial print statement, so it's easy to disable those. Hopefully I've added lots of comments so people can modify the code easily for their own hardware enhancements. So let's take a look at the Arduino interface here. Now there are a couple libraries that you're going to need to install. One is the PS3 controller library, so you can go to the library manager. This is the one you need to install. There's also a library for servos called ESP32 Servo. It's written by Kevin Harrington and John Bennett. It's at 1.21 at the time of this video. And you also are going to have an ESP32 board, and you'll find that you need this this library here, ESP32 by Espressif Systems, and you're going to need 2.0.17 installed. Do not update to 3.0.0 or your servo library will break. At least it will break at the time of this video, which is May 2024. You want to pick the ESP32 dev module as your CPU, and you should see a serial port listed. I'm in a Mac, running Mac OS here, and yours on a Windows machine may be different, or even if you're in a Mac machine, maybe a different number here, but you do not want the Bluetooth incoming port here. So those are the major setups for getting this to work. So we'll start with a bunch of comments, but basically we have a couple controllers, libraries that we need to run at the start. Now first we'll look at what this debug does. Now normally, in order to get feedback, you would use a serial.print command, and you might print the value of something like bucket, let's just say counter. Let's suppose I have some variable called counter. And I would use a statement like that, and it would print, when connected to my Arduino interface through my Mac, it would print that back to the serial monitor so I could see it on the computer and I can see some values. But one of the problems is that once you leave these statements in, even when you disconnect from your computer and you're running it just standalone, the serial.print statements are still being executed, and if you have a lot of them, you don't need that computer doing that. So right here, I've got a conditional compiler statement, and what it does is instead of using serial.print, I replace this with debug. So I might want to print debug counter. And this block here will do a few things. If I have this defined statement as a 1, it replaces all debug statements with serial.print. So this basically gets replaced by serial.print, and I get feedback out to my computer. But once I've got it all debugged and I'm ready to compile this for my final version, I know everything works. If I put this to a 0, then all these debug statements, they don't get replaced by these. Debug's no longer 1. It'll go down to the else statement. It'll define the debug, nothing here, just to a null statement. So it's effectively just like this statement doesn't even exist. So in my final version with this 0, basically all my serial.print statements disappear. So my little ESP32 is no longer sending things out through the serial port unnecessarily. So these define the pins that I'm using for the bucket servo, and this comes from my version 2 of the PCB. If you have a different PCB that uses different pins, you would just change that here. This command here creates its object-oriented command. It creates an instance of the servo object called bucket servo and another object called claw servo. And once we have those two objects, we can do various things with them. We can attach them to pins, we can write to them, and so on. Now this code supports proportional throttle, meaning the more I position the joystick up, the faster my little skiddy will go. If I want that proportional throttle, I just set this true. However, if I just want it to be full speed or stop, you can set this false. I have a little red flasher on top, and if you have built one as well, you can set this true. Otherwise, you just set this false, and it disables the code for the flasher. These are the minimum and maximum values for the servo. You have two servos, one that moves the claw open and close, and one moves the bucket up and down. And these are the values which work for my servos. But every time I change servos, I need to change these values. Almost every servo is slightly different. So you can tweak these values right here and compile it and run it with your Skiddy attached, and you can see the effect of these as you change them. Basically, you want to make sure your servo doesn't go too far. It should stop in software before it hits a hard endpoint, meaning something that will prevent it from going further. So for instance, once the claw closes, if it closes at 80, you don't want to set this to 60 because it would be straining to get to a position it can't get to, and that will cause the motor to burn out. Servo update is just a value to delay servo responses. If you don't do this, these servos move very quickly and your bucket and your claw are just going to move too rapidly. So we put a value here, and it's like a little counter. We're going to go through, we're actually going to count to 1,000 before we make in between writing to our servos. If you find your servo's moving too slowly, you can reduce this. If it's still moving too fast, you can increase this value. You wouldn't change this value here. This is the same for the flash. You shouldn't really need to change these though. This basically gives you an on and off flash for your red flasher on top if you have it. These are initial values for your bucket position on boot up and your claw. You can change those. If you want your claw to be closed, you could put this to a value that would be more closed. These are all the pins that I'm using for my motors. And so the first two are my right motor pins, 0 and 1. The next two are for the left motor, 0 and 1. The next are the the arm motor. So I have 21 and 19. And finally, the aux 0 and 1 are these two. If you have different pins you're using, you can change these here. If you find a motor's going backwards, let's suppose my right motor, when I hit the throttle forward, it's going backwards, you can actually change the position of these, 26 and 25. And that should take care of it, as opposed to changing the wiring on the connector block. Sometimes easier to do in software. These variables here I call flags or semaphores. That's what we used to call them. Flags, they just have one of two values, true and false. And they're used to indicate whether my lights are on, whether my claw servo should move up or down, whether the bucket servo should move up or down. We'll see how they're used later. Now, there are three main routines inside this. We first have something called a routine called notify. And this is running on an interrupt basis. Or I believe it's running on an interrupt basis. This is the start of it. And probably running every so many milliseconds. We'll say, for example, it might be running every 1 to 10 milliseconds. And it's going to poll your joystick. And so there's statements in here to just check every joystick position and every button to see if they've been pressed. And if they have, you will do something. That's the main routine that's going to handle your joystick interaction. Now, the sections of code, the main sections of code, are the initialization, which is all this stuff here, setting up your variables and your defines. You're then going to have a block of code that is going to be called setup. And it's going to be used for anything that's run once as your device boots up. And then after you've done your setup statements, you have a loop, a bunch of code statements. And this is not interrupt driven. It's just going to execute all these statements and then it's going to loop around. And so this one is called loop. So those are the four sections that this code is broken up into. So in the notify code, you'll notice there are all kinds of debug statements that you can use when you press a button. You should get something back on the serial monitor to indicate that button's changed. And here is where you do events. So this code here, LX means the left joystick in the X direction. So if I'm moving the stick left or right, I'll get a value here. If I'm moving the stick up and down on the left joystick, LY will have a value. So if I drop into this code here, it means that I've moved that left joystick. And here I'm getting the values of the left joystick and the right joystick. And these values are integer values. They're called signed integer values because they go from -127 all the way to +127 in value. Now, if I look at the X value, and it's between minus 20 or 20. Basically, my joystick is in the middle. I'm not going left or right. Sorry, let me rephrase that. If my value is less than minus 20, so we have minus 127, minus 20, 0, 20, 127. So if I'm in this region, I want to do something. I'm assuming my joystick is turned to the left or right, and if I get a value in this area, I know that I want to turn in the other direction. But anything in between here, I'm going to assume that's basically a stop. So if I know my joystick has changed position here, I'm going to go down here and I'm going to set a flag. Depending on if the value is greater than 20, I know I want to turn left. So I set a flag to tell me to turn left. I'm then here going to find out, do I want a proportional throttle? And if I do want a proportional throttle, I'm going to get a value, and that value is going to be between 0 and 255. So what I need to do is change this number from 0 to 127 to a value from 0 to 255, because that is what the PWM pin is going to put out to the motors. So 255 represents full power, 0 is a stop. I take the absolute value because sometimes the joystick will give me a minus number, minus 127. So that's basically full power, but going left instead of right. So absolute value, change that to plus, multiply it by 2 to get that as a maximum value. Now once I know I want to go forward, or sorry, once I know I want to turn left, I want to change both the right and the left motors. And we'll take a quick view to the bottom of this code to look at my motor routine. So at the very bottom, I have a motor routine that writes to two motors, and there's 4 inputs. Each motor has a 0 and a 1 input. So this writes to the right motor, this writes to the left motor, so I have 4 values. So for instance, if I put this at 255 and this at 0, that may cause the right motor to go, say, forward. If I reverse it here, this will go in the reverse direction at full power, and so on. So let's go back up to our code. And so if I know I want to turn left, these are, I basically am applying a number for power to this input, with this one being grounded, and on the left motor I apply power to this input, and that will turn to the left. I do the reverse of that if I want to turn to the right, so the else statement is just doing that. Now, if the joystick is not pressed in the X direction, there's an else statement here to check to see if the throttle was pushed. So do I have a Y value that is not stopped? Has the user pressed the left joystick either up or down? And if I have, I want to come in here. And the first thing I want to do is, well, which way did they press it? So I have a little flag here to say go forward. So if the value is less than minus 20, I know I want to go forward. You don't need to worry about these statements. Power here is the absolute value times 2. I'm getting a power value here. Remember, I'm getting this minus 127 to plus 27. I'm changing that from a number to 0 to 255. And then if I'm moving forward, these are the statements here which will allow the motors to get the power to move it forward. If you set this flag true, that means you've got a flasher, and all this code does here is turn on or off a flasher. Now if we're moving forward, we don't want the flasher to be on, so what this does is turn the flasher off. And it sets a flag false here. You don't need to worry too much about this. This should sort of work on its own. But basically I have two motor inputs, and those two motor inputs are going to be connected to a flasher LED, which is just an LED with a current limiting resistor. And if this is high, say plus 8 volts, and this is low at ground, current's going to flow through there and turn the light on. If this is low up here, so I have low, low on both inputs, this is going to be off. If this is high, current cannot flow back through the LED. That will also turn it off. Now moving backward, we have the same thing. This is the sequence of applying power to have it move backwards. So this power, if you're not using proportional throttle, power will always be 255. But if you are using proportional throttle, I convert it to a number between 0 and 255 so that it will go slower. This is a section which only happens if this flasher present is true. And what it's going to do is we've started to move backwards, so these two statements right to the last two pins in the motor array, which are the aux 0 and aux 1, a low and a high, and it turns the flasher LED on. And then I'm going to use a counter to know when I should turn the flasher off. So I'm going to turn the flasher on. I'm basically going to count up to a number. I count to 2000, then I'll turn it off. Then I'll count to 2000 again, turn it on. So that regulates how fast or slow the flash is. Now, if neither joystick if the joystick on the left is not pressed up and it's not moving side to side, then really I should turn off all the motors. I also want to check that if the flasher was present, and if I'm not backing up, I might want to turn my flasher off. So this code's going to do that. But it's only going to do it if you have a flasher in your hardware. This code here moves the arm motor, and here we're doing digital writes instead of analog writes. So we're just moving the arm with full speed up or down. The arm has to have a certain amount of torque, and it doesn't work too well if you try to use PWM or analog writes with the arm motor. So if I look at this right joystick, so I get an RY value. So this section here is only going to get executed if my right joystick has moved. So my RY value means I move the right joystick up or down, and if the value is greater than here, I'm using 115 instead of 20. I guess half the joystick, sort of halfway. And if I move the joystick hard up, then my arm should go up, and these are the settings that make my arm go up, and these are applied to the arm motor inputs. I reverse that if I want the arm to go down, so else if it's less than this. Now, if I've moved the arm, and then my joystick is now in the middle, I really want to stop my arm. Well, I use what's called magnetic braking to stop the arm. What I do is I apply both highs to the inputs of this motor, and they'll magnetically brake. I didn't do that, if you go back and look, I didn't do that with the drive motors. I use two settings, low, low, which coast motors, and that's generally what you want to do on drive motors. So if your Skiddy's driving along and you all of a sudden put the joystick in the middle position, you don't want it to suddenly just stop and brake hard. It'll just coast to a stop in a few centimeters. But with the arm motor, if you coast it and you're lifting something up, so you've got something in your claw here, You're lifting it up and then you're putting it down. You've got your claw here holding it up. You may find if this is too heavy, if you coast your motor, this may drag the arm all the way down. So I use magnetic braking to help stop the arm when it's descending. I may want to stop the arm halfway down, and if you put high and high, you'll see the difference if you change these. If you change this to low and low and then try to pick up something, lower it that's fairly heavy and then stop it midstream, you'll see the difference in these two. And you can decide which you want. You may want these two to be low, low, but you have that option. Now these are the buttons, and the buttons on the end of the controller are used to move either the claw open or closed and move the bucket up or down. We've got two flags that indicate what I should do. So if I press this button, this indicates I want to move the servo up, so I set a flag here to true. If the button's released, I don't want to move the servo up anymore, I set that flag to false. Now I'm not actually doing any work inside this routine. This is an interrupt routine. You generally want to do the work outside of interrupt routines if you can. You want the interrupt routine. Interrupt routines should basically work as fast as possible, because in another millisecond they're going to get fired again. So if you're busy doing work and you don't finish all the work here and it fires again, you're going to get, your interrupt routine is going to get interrupted by itself. Another interrupt routine is going to fire, and you're going to have these nested routines which are being called. And if it happens too much, you could run out of RAM. So you want those to execute as quickly as possible. We've also got some flags for the claw servo, whether that's going to be open or closed. They've used up and down here, but really it's whether I'm going to open or close it. So all we're doing right now is just setting flags true or false, indicating what I want to do, whether I want the bucket to go up or down or the claw to go open or closed. And really, that's it. Now, if I have the right joystick and I press that down, there's a little click, and that click causes this routine to fire. So it's a down button on the right joystick. I had a hard time finding it. And if you do that, you'll want to turn your light bar on. There's little lights in the front of the cage, like headlights, if you have them. Now you only want the lights to go on if you don't have your backup. If you have a backup flasher and it's flashing, you can only do one of two things, because I have a single output controlling the flasher at top and the headlights. So I've got to have a priority. My priority is the red flasher on top. So if you have that, you can't turn the front lights on. So these get disabled, but only if you have a flasher and only if it's flashing. Otherwise, when you press that button down, your lights will go on if you have them on the front of your cage. And to turn lights on, you simply write to the lights output, a digital write of high and low will basically apply a plus signal to the LEDs that you have there. You may have two LEDs, it's a resistor, and you're putting a low here so the current's going to flow through the LEDs and turn them on. This little flag here keeps track of whether the lights are on or off. So if the lights, if this is false, this means the negative of it. So if the lights are not on, this turns lights on. Otherwise, I'll turn the lights off. And if I turn the lights off, then I'm setting that flag to indicate, the lights are off, so I'm setting that false. Here I turn the lights on, I set that flag to a true. And that's the end of that routine. The setup routine here is only running once. Now this is fairly interesting here. What you'll find with a proportional throttle is that if you just use the stock PWM frequency, so PWM means we've got a square wave signal like this. So this is the period of that signal, and we're just varying. The signal always has the same period or frequency. We're just varying the width of how often this is on. So this is on high longer, so it's going to go faster. If I'm on this short period of time, it's going to go slower, but my frequency is always going to be the same. So what frequency should we use? I think by default it uses something fairly low, like 100 Hertz. But one of the problems is it makes a squeal or a whine at very low speeds. If you put the frequency up around 10,000, you may find your motor works a little better. Some motors work better with different PWM frequencies, so you've got to sort of test it. 10,000 Hertz, I don't hear a squeal, and it seems to work fairly well. So that's one of the changes I made to that. This is the frequency of your serial port when you're getting signals back from the ESP when it's connected to your computer. And this is just stuff used by the PS3 controller to connect to. Now, remember I said you had to set an address for the ESP32 Bluetooth controller. Here's where you set this. So you use that little 6-axis tool to program your controller, your PS3 controller, to have this address. And really all that's doing is telling the PS3 controller, I want to pair with this address. Here's where you set the address inside the ESP32. So now the controller will look for this address. The ESP has this address, so it's going to respond and they'll pair instantly. These are two little statements where you can check to make sure, well, I tried to set this address, but did it really get set? And you can, in these debug statements on your computer, you'll see if that address got set properly inside the ESP32. If you use something weird here for an address, the ESP32 may say, no, I'm not going to set it to that address. There's something wrong with that address. This statement is just a little for loop, and it sets all my, basically my motor outputs to in the output stage, meaning I'm going to write to them and it's going to be connected to something like a motor. Here's where I actually attach the servo pin. I tell this servo object, this is the pin you're going to use, your claw, what pin you're going to use, and then I'm going to write, this is the value that I set up there for the boot up value. If I put a value of 150 here, my bucket servo will immediately go to that position. Now remember I said I had a loop that works forever. This is where work is actually being done. So if my flag to move the claw servo up is true, that means I want to move that claw servo up. So there's a little delay though. There's a counter here. This is a counter. And every time through here, it's just being incremented by 1. That's what this does. And when it gets greater than this value, it might be 1,000, which I put up there, I'm going to say, okay, I've waited long enough. I'm going to actually write to my servo now. So my claw servo value, and I assume that the claw servo value or the position of the servo is less than a maximum. These are the end stops. I don't want it to go too far. If it is, I'm going to increment my claw servo value and I'm going to write that to my servo. My servo is going to basically move a little further in one direction. Then I'm going to go through this loop again. I'm going to count to 1,000, and once I get to 1,000, I'm going to say, hey, have I reached the end point? No, I can still go further, so I'm going to increment the claw servo value. I'm going to write it, and my little servo is going to go a little bit further. As long as I've pressed that button, if I release the button, this flag gets false, and I no longer go through this routine. Now there's also a flag to move the server down. It works exactly the same way. If this flag here is set, that indicates I want to move the servo down. I'm doing all the same things except I'm decrementing. All this is subtracting 1 from this class servo value. So this routine is just moving the servo in the other direction until it gets to this minimum value, and then it won't decrement it anymore. It only decreases it as long as it's still above this minimum value. So that's the claw servo. We have identical thing happening to the bucket. I have these 2 flags to move the bucket up or down using exactly the same type of code. If I have a flasher, so if my flasher's present, I do the same type of thing here. I'm also counting so often, and once I reach the end of whatever my flash update counter is set to, I'll actually toggle. So flag flash on equals negative. Basically, I'm toggling my little flag here, which is basically this is going to change from a high. When I toggle something, it's going to go from high to low. When this is low and this is low, my flasher light is off. When this is low and this is high, my flasher light is on. So I'm going to count to 1,000. I'm going to put this low high, and that the way electrically my little flasher's connected like that. So that's going to turn my flasher light on. Then I'm going to count to 1,000 again, but I'm going to change. I'm going to toggle my flag, and that's going to cause this to go low, and that's going to cause no current to go here, so my light will go out. And I just continue doing that as long as a little flag here says, yeah, I want you to flash the backup flasher. And that's it. Really, this is last part is just checking to make sure the PS3 controller is still connected. So hopefully that gives you some idea of what happens here. You may need to use some of these print statements to see how everything is getting executed, but hopefully you'll add your own modifications and have fun with this code.